Okay, organic chemistry 2341. We're going to continue on with chapter 11. This is video number 2, specifically reactions with alcohols. Okay, so as we said before, alcohols are the group that has an OH group attached to an sp3 hybridized carbon. If we have that hydroxy attached to an sp2 hybridocarbon, we call them enols or phenols, or an aromatic alcohol here. So those are slightly different. Those are the only two systems that have an sp3 hybridized. Most of the other systems have sp2 hybridized. Okay, so when we talk about nomenclature for alcohols, we learned it originally in chapter 4, but just to remind you there, alcohol takes the name of the compound, and therefore if we have a propane group with an alcohol in it, it'd be propanol. In the case of having an alkene or an alkyne in the system, an alkene and alkyne kind of share priority with alcohol. So if we have an alkene and an alcohol, we call it an enol. So in the case of this compound here, we have what we call 1, 2, 3 carbons. So that's propene, but it's propene 1-ol. If we have an alkyne, alkyne also shares a name with it. So it'd be propyne 1-ol. Okay, so that's the subtlety in the naming of alcohols, where we have a shared alkene or alkyne. The rest of the time, alcohol does take the precedence until we get to higher order substituents. Okay. So in chapter 8, we learned a bunch of different ways to make alcohols and ethers, mostly from alkenes. So we could do a hydrolysis of alkenes to give us, and by doing it in a variety of different ways, we can get to our tertiaries by going through a carbocation. We can get to our secondary by limiting the carbocation rearrangement. And we can also get to our primaries by doing a hydroboration oxidation reaction, where we get the boron attached to the outer carbon, and then we get oxidation of it off with peroxide to give us our primary. So using our addition reactions here of water across an alkene, we can get to our primary, secondary, or tertiary alcohols. Okay. We can also get to these alcohols and ether via substitution reactions. Okay. So we talked about being able to create ethers from these alkyl halides. Now let's talk about getting alcohols from alkyl halides. So if we have methylene primaries, we can use SN2 reactions with just hydroxide as a nucleophile to give us our alcohol groups. Okay, so one of the reactions we have associated with alcohols is we can then actually convert them from alcohols back to alkyl halides, okay? However, we cannot do this directly. If we just tried to hit it with a nucleophile, we would have hydroxide as a leaving group. Hydroxide is a very poor leaving group. So in general, we would typically use a strong acid to do this, because the strong acid would first protonate the alcohol, making it into a hydronium ion, which makes it a much better leaving group as neutral water. Okay, so when we use reactions with very strong acids like HCl, HBr, or HI here, we can get primary, secondary, or tertiary alkyl halides to form from them. Okay, so in the case of this, when we have HBr, we can displace, we can add proton to this here and then displace neutral water from it, giving us our alkyl halide. Okay. So, but going from a primary, secondary, or tertiary alkyl halide from these alcohols involves different mechanisms. Okay, so let's look at that a little more closely. So if we have a primary alcohol or a methyl alcohol, they're going to be less reactive than a secondary alcohol, and the tertiary alcohol is going to be the most reactive. And it has a lot to do with what the leaving group is, okay? In all of these cases, we're using a strong acid, HCl, HBr, or HI, which means the first step is always going to be the protonation of the alcohol, giving us our H2O as our leaving group, our good leaving group here, and then whatever it is to use as our nucleophile displaces it. In the case of primaries and methyls, we go through an SN2 reaction, and therefore we get inversion of stereocenters. In the case of tertiaries and secondaries, we go through an SN1 mechanism, i.e. carbocation. Therefore, we get racemization of that stereocenter. So think methyl in primary as SN2 and secondary and tertiary as SN1 mechanisms, okay? So as such, that means that the stronger the acid, the more nucleophilic the conjugate base is, therefore the higher the reactivity, okay? So HCl is the least reactive of the set, followed by HBr, and HI is the most reactive of the set. In fact, chloride ion is such a poor nucleophile in protic solvents, we have to add a Lewis acid catalyst to get it to go. And the reason this works is that instead of just protonating the alcohol, we actually have the zinc complex to the oxygen in the alcohol to generate an even better leaving group than before. So the poor nucleophile of chloride in a protonated solvent, because we have an acid, it will be able to displace that, giving us a zinc hydroxide chloride. There's only one chlorine here, actually, so that you can get this through. And again, because it's a primary alcohol, we're going through an SN2 mechanism. Okay. So because it's so difficult to do the primary alcohols that way, we actually have other reagents that we can use. So we can use, instead of the acid halides to generate a chloride, we can actually use a compound called thionyl chloride, SOCl3, as our reagent to make primary and secondary alcohols into alkyl chlorides. Okay. Now, the reason it works is we're making that alcohol into a much better leaving group. We're not just protonating it and making it into water. We're actually using the electrons on the alcohol to add to this sulfur-oxygen double bond to give us a sulfonyl ester compound. This sulfonyl ester is a very good leaving group once it's deprotonated by a base like pyridine, and therefore we can have the chloride come in and displace it to give us SO2 and chlorine ion, which is, guess what we needed for our reaction here anyway, and our alkyl halide. And so this chloride can then be used as a nucleophile on another compound. Okay, so the idea is we're taking our primary alcohol or secondary alcohol and turning it into a much better leaving group while still generating the chloride nucleophile in the reaction. Okay, so if we wanted to convert to a bromide compound, instead of using SOBr2, we actually use phosphorus tribromide, okay? So this will make primary or secondary alcohols into alkyl bromides, okay? And the way it works is kind of similar in the fact that our oxygen binds to the phosphorus, making this intermediate phosphorus group into a very good leaving group. And then we can get displacement by our bromine to liberate our new phosphorus oxygen compound here and our alkyl bromide. Again, this works by primary and secondary because it doesn't form a carbocation, it actually goes through an SN2 mechanism. Okay, so the review of all the different ways to prepare alkyl halides from alcohols. If we have primary, secondary, tertiary alcohols, we can use HI and HBr to convert them to the alkyl halides of choice. If we have a primary alcohol and we want to turn it to the chloride, we must use zinc chloride as an activator. If we want to convert it to a bromide, instead of using HBr, we can actually convert primaries and secondaries to the alkyl bromides and the chlorides using the phosphorus derivatives here. And we can make primary and secondary alkyl chlorides using thionyl chloride and its primary or secondary alcohol. Okay, in the previous chapter, we actually learned a way to make syn dihydroxy compounds. And we had two ways to do that. We could oxidize a carbon-carbon double bond using potassium permanganate, or we could add osmium tetroxide across that double bond and then oxidize that off again to give us our cis-diol compounds. Now, here we're going to learn a way to make the anti or the trans-diol compound. So in this case here, what we're going to do is we're going to take our alkene just like before, And then we're going to use what we call a per acid. Notice there's CO3H here. That means there's an extra oxygen in our carboxylic acid. And that extra oxygen is going to be added to this double bond here, creating our cyclic ether. Remember, we waited to do this because this is our cyclic ether section. We introduced this 3-membered ring in our first video, and we're going to talk about it in our 4th video too. Once we create this epoxy right here, we can use a protonated water to go ahead and act as a nucleophile and open the ring up, but it has to open it from the opposite side. So we end up with the trans dialcohol compound. So the idea here is that we have the hydronium ion gets protonated by, the epoxy gets protonated by the hydronium cation portion here. Now water comes in and acts as a nucleophile and opens it up, and then we, of course, transfer a proton at the end to get to our neutral species. This always gives us our anti or our trans hydroxy products because the nucleophile has to come in from the other side, opening up our 2-alcohol system. And we'll talk about more about that kind of nucleophilic attack in video 4. All right,